Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your ZyBooks Section 5.2 titled Boolean Functions. So, do you remember truth tables from Chapter 1? Where you had propositions that made a larger compound proposition, and then you made a table where you listed all possible inputs, all possible truth values for the individual propositions, and then what would be the truth values for the compound proposition. Similar here. We're going to be looking at Boolean functions, where most of the time we'll be taking a look at some tables with all possible inputs in one side of the table, and then in the last column you'll have the outputs of some function. Right, and then what we're going to be doing in this section is determining what does that function need to look like? What expression has those outputs for all these possible inputs? Right, hopefully you'll see what I mean when we get to this section. Alright, so a Boolean function maps one or more Boolean input values to the set 0, 1. So let B be the set 0 with element 0 and 1 in it. Then B to the k, remember this is the B cross B cross B cross B, is the set of all k tuples over the set B. A Boolean function with k input variables maps B to the k to set B itself, right, to the set with 0, 1. So it takes some input and maps it to either 0 or 1. One way to define a Boolean function is to provide an input-output table that shows the output value of the function for every possible combination of input values. So consider the Boolean function f from b3 to b, where again it's just so they're going to take bit strings of length 3 as an input, and the output will be either 0 or 1. And the function f of x, y, z, because again there's the input should have 3 components, right? It's b3, and the output will just simply be 0, 1. The function f of x, y, z is defined by the following input-output table. So this is telling me the input 0, 0, 0 maps to 0. The input 0, 0, 1 maps to 0. The input 0, 1, 0 maps to 0. 0, 1, 1 maps to 1. 1, 0, 0 maps to 1. 1, 0, 1 maps to 1. 1, 1, 0 maps to 0. And finally 1, 1, 1 maps to 1. All right. So a Boolean function with k input variables will require an input-output table with 2 to the k rows, right? See that this had 3 input variables, right? X, Y, Z. Notice how it has 8 rows. Remember, just like truth tables. Remember truth tables? If there were 3 propositions, P, Q, and R, then a truth table had 8 rows, 2 to the 3rd power. Same thing here. Same thing here. Because there are 2 possible values, for each variable, 0 or 1. So 2 times 2 times 2 is 8. It gives you 8 possible inputs. Now 2 to the k is very large even for modest values of k. So using a table to define a Boolean function is only feasible for functions with a small number of input variables. Alright, because if there were 4 input variables, then all of a sudden you'd have to have a table with 16 rows. I mean, that's pretty big. And then 32 rows and 64 rows. Right? It gets unwieldy pretty quickly. Alternatively, one could use a Boolean expression to define a function. Right? The function above, right, this function here, is f of x, y, z equals x times the complement of y plus y times the complement of z. Alright, so this expression, x times y bar plus y times z, has the same, all these values here, the 0, 0, 0, 1, 1, 1, 0, 1, has these values when you plug in these inputs on the left three columns. Alright, so if I plug in 0 for x, 0 for y, 0 for z in this expression, I'm getting an output of 0. Alright, if I plug in 1 for x, 0 for y, 1 for z in this expression, I'm getting an output of 1. Right? So this table is represented by this expression here. And you could almost think about it as a truth table for this expression. Right? X, y bar plus y times z. Alright, and let me show you how you can put that together. And I'll come back and we'll compare it to this table here. I'll show you on paper how it's basically exactly like a truth table, how we constructed truth tables back in chapter 1. Okay, so here's that expression that was mentioned in that example in the book. F of x, y, z equals, x times y bar plus y times z. So if I'm making an input-output table, you got the Boolean variables that show up here are x, y, and z. And as mentioned earlier, there are 3 of these, so there's going to be 8 rows, right? 2 to the 3rd power. All right, and down the first column, I'll break it, 8 in half. We'll go 4 and 4. 4 zeros, and then 4 ones. Then the second column, I'll break 4. Take 4, break that in half. Do 2, do 2, then 2, then 2, then 2. I'll do 2 zeros, then 2 ones, then 2 zeros, then 2 ones. And then break 2 in half and do 1. So just alternate every 1 for the z column. 0, then 1, then 0, then 1, 0, then 1, 0, then 1. And there. This is all 8 bit strings of length 3. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. All 8 possible inputs when my variables x, y, and z can take on the value 0 or 1. Now, you could just take this expression here and plug these in and tell me what the output is. All right. But if we, you could also do, that might take a while. I mean, this expression isn't that big, so it would be pretty easy to do. But another thing you could do is like our truth tables before. I could make a column for not y, right, the complement of y here. And I'll do these in different colors. Right. So not y, the complement of y would be 1, 1, 0, 0, 1, 1, 0, 0, right? If I just do the opposite of the y column, then I make a new column with the x times not y, x times not y here, and just pay attention to, I'm doing the x times the not y column. So this first column and this fourth column, I'm multiplying these values. Now remember, the only way this is going to be 1 is if they're both 1, otherwise it's going to be 0. So 0 times 1, 0. 0 times 1, 0. 0 times 0, 0. 0 times 0, 0. 1 times 1 is 1. 1 times 1 is 1. 1 times 0, 0. 1 times 0, 0. Alright, that's for the x times not y. Then for the y times not z, or just y times z, sorry, just y times z. I'll make a column for that. Now again, that's the second and third column I'm multiplying. So 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1. 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. And 1 times 1, 1. Alright, then finally, in the last column, which I'll do in a different color, we have our function. Right, this x times y bar plus y times z. So I'm taking the x times y bar column and adding the y times z column. All right, so I'll do this in like an orange. I'll do it in like a purple. All right, so I'm looking at these two columns, and now when I add, if any of them is a 1, the sum is 1. So 0 plus 0 is 0. 0 plus 0, 0. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 0, 1. 0 plus 0, 0. And 0 plus 1, 1. Now look at this column here. This is my final product. These are all the outputs. All right. So again, these are the inputs. All right, these triples over here, and this one column is the outputs. And let's compare that to what I had. It was 0, 0, 0, 1, 1, 1, 0, 1. And look back at the website, you see this, 0, 0, 0, 1, 1, 1, 0, 1. Beautiful. It matches. All right. So you could make, if you're given an expression, if you're given a Boolean function, a Boolean expression, you could make a table for it, just like you did with truth tables back in chapter 1. Or just plug in all the inputs and see what the outputs are. Same thing. Alright, so see, given a Boolean function with k input variables specified by a Boolean expression, it is not hard, although it might be tedious, to fill out the 2 to the k rows. You saw that. It took a while for me. It is not hard to fill out the 2 to the k rows of its input-output table for that function. Is it possible to go in the other direction? All right. That is, if we're given an input-output table defining the values of a Boolean function for each combination of inputs, is there a Boolean expression that specifies the same function? So this is the other way around, right? See, what I did on paper a second ago was I was given the function and then I made the table. What we're going to be doing now is, if I'm given the table, can I write the function? All right, and it's really not as difficult as it seems. All right, so I'll play this animation for you. What you're going to be doing to write a function for a Boolean expression is focusing on when the value is 1. When the value is 1. All right, so let me show you here. So see, it says, to find an alright, so here they give us this table, the same table as earlier. To find an equivalent Boolean expression for function f expressed by a table, first find the rows in which the value of f is 1. Right, so we got the 4th row, 5th row, 6th row, and 8th row. Okay. Next. Now, f is 1 when x is 0, y is 1, and z is 1. Right. Now, what we're going to do is turn each row. Right? You're going to turn each row with an output of 1 into a product involving the 3 input variables. Right. Now, remember, the only time a product is going to be equal to 1, the only time you multiply things and you get 1 back, is when everything is a 1. So here you see x is 0, y is 1, z is 1, so I'll keep y and z the way they are, but x is 0, so I'm going to take the opposite of that. See, that's why they have the opposite, the complement of x, and then times y and times z. So they kept y and z the way they are, and multiplied by the opposite of x, the complement of x. So this product will give me an output of 1 when x is 0, y is 1, z is 1. All right, and we're going to do this for every single row. So for the next row 5 here with an output of 1, and I'm going to write a term that's a product of x, y's, and z's. Now x is 1, that's fine. I'll keep x the same, but y and z are both 0. So I'm going to do the complement of y and then the complement of z, as you'll see. Right? So you see 1, 0, 0. So I keep x the way it is because it was a 1 already. but then the two zeros, the y and the z, I'm going to use their complements. X times the complement of y times the complement of z would give me that output of 1. And then for the next row, x, the complement of y, and z. And I'll have the product of those. X, the complement of y and z. And then for the last row, when the output is 1, x, y, and z are already 1, so I'm just going to use x, y, z. And then you add these together, and there's your function. Because what you're doing is writing down all the scenarios where the value is 1. So it's either this scenario, or this scenario, or this scenario, or anytime you hear the word or, you should think addition. So it's this plus this plus this plus this, and that takes care of all the scenarios where it's 1. Therefore, anything that's not one of these 4 scenarios, the output will be 0. So you do take care of the entire function this way. All right. So I add those different products together. So you see f of x, y, z. The function here is x bar y z plus x times y bar times z bar plus, now that's y bar times z bar, not y bar z, not y z bar. There's 2 separate bars there, it should be. Plus x times y bar times z, and then plus x, y, z. And then we could show through some laws, right? We could show through some laws that this is actually equivalent to the expression they had here, x times y bar plus yz. Right. Okay, but that's how you create a function from a table. Now there are some names to what was done up here. So here is a formal description. So they gave a description of the process that constructs a Boolean expression that is equivalent to a Boolean function defined by an input-output table. So first, some definitions. A literal, right? A literal is a Boolean variable or the complement of a Boolean variable. So for example, x would be considered a literal. The complement of x would be considered a literal. All right, so it's just a single Boolean variable or the complement of a single Boolean variable. It's called a literal. In a Boolean function whose input variables are, say, v1 through vk, all right, so k variables, a min term, all right, a min term is a product of literals u1 through uk, such that each of these u1 through uk is either v1 through vk or the complement of v1 through vk. Alright, so that's all that's saying. Like all these up here are what they call min terms. So you see the input variables are x, y, z, and this first term is, x bar, a literal, times y, a literal, times z, a literal. Alright, so every single min term is a product of literals involving all the input variables. Alright. Alright, so you should be able to express any function if you're given a table. You should be able to express any function as a sum of min terms. And each min term is a product of literals. All right, some fancy words. Okay, so let me do that with this. All right, I'm going to actually write this down, and I'll show you how I would develop an expression for this function. All right, the function represented by this input-output table. I'll do this on paper. Okay, so here I have written out that same table from the activity. We have, again, 3 input variables, x, y, and z. So you see that, again, the 8 rows, the 8 possible inputs, right? So these first 3 columns give me all the inputs of this function. And then this last column, right, is the column of outputs. All right. What I'm going to try to do is, write a function. What is an expression for this function? F of x, y, z here is equal to what? I'm trying to figure out this expression that would take on all these values when the inputs are all these, right? So as in the last animation, to do this, given a table, can I write a function? We look at every row where the output is 1. Right, just focus on the ones. And then in each of these rows, we're going to create, again, what's called a min term. A min term is a product of literals of these input variables. So you'll have either x or x bar times either y or y bar times either z or z bar. Okay. Now remember, I want the product, I want this min term to give me a product equal to 1. Well, in this row, it's 0 times 0 times 0. Well, that's not giving me 1. Right? The only way you get a product equal to 1 is if the value of every factor, every literal, is 1. So 0, 0, 0, change all these into 1s. So I'd do the complement of x times change that to a 1, the complement of y times the complement of z. So x bar, y bar, z bar. Separate bars, do not connect them. So here's the min term for the first row. Give me an output of 1. And I do the same for each of the scenarios that the value of this function is 1. Right? So the min term for this row, this fourth row. Now the value of x is 0. I want it to be a 1, right? Because I want a product equal to 1. So I take the opposite of that, x bar, times, and then y and z are both 1 already in that row, so I'll keep y, keep z. Okay, so there's the min term, the product of literals for the fourth row. And I do the same for the fifth row. The min term for the fifth row. Again, the x is 1, so I'll keep x the way it is. Y is 0. So I'll take the complement of y, right, times y bar. And z is 0 in this row, and I'll take the complement, take z bar. So again, these are separate bars. So this is x times y bar times z bar. And finally, the only other scenario where the output is 1, the min term for this seventh row, x and y are both 1. So I'll leave those the way they are. Z I change into 1 by taking the complement. So the min term for this last row is x times y times z bar. Alright, so then this takes care of all the scenarios in which the output is 1. When is the output 1? Either in this situation, or in this, or in this, or in this. So I add all these up. And if that takes care of all the scenarios when the output's 1, then that means all the other inputs will give me an output of 0. So the function is complete. So we have the expression for this function is x bar, y bar, z bar, again separate bars, right, plus x bar, y, z, x bar times y times z, plus x times y bar times z bar, and then finally plus the last scenario where you have an output of 1 here, this min term, x times y times z bar. So here's an expression for that function. Right. So if you were to plug in 0 for x, y, and z, the output would be 1. If you were to plug in 0 for x and y and 1 for z, the output of this would be 0. And you can test it. You can test all 8 of these in this expression, and you'll get these 8 outputs. Now, this is kind of ugly, right? This sum of min terms, but it still works, right? Now, we're going to be in the future, we're going to take this, sum of min terms here, and then use our laws of Boolean algebra, which you saw in section 5.1. We can use some laws to really simplify this stuff. Okay. But for right now, I'm going to leave it the way it is. Okay, so back on the activity. Is x times y a min term? No. Remember, a min term is going to involve all the input variables, x, y, and z, or their complements, x bar, y bar, or z bar. This does not involve z. So, no. Right, a literal for z is missing. What is the min term? I already did this, right? Corresponding to the 7th row, that was x, y, z bar, right? X, y, z bar. And then which, I already, again, rows 1, 4, 5, and 7 are the ones I use to create the function, create the min terms. And then what is it? And I wrote that one up as well, and that was this one here. All right, so you're asked to do the same thing for 5 times. Here's an input-output table. Write a function just as a sum of min terms, right? Write in the sum of min terms form. Don't simplify it with laws. So I'll just do the first couple. Now notice, instead of bar, see, you're going to type an apostrophe, x apostrophe for x bar. Okay. So here, where is the output 1? Just in the first row. So this function's only going to have one min term, one term. And the min term for this first row would have to be x bar, y bar, right, to make both of these into ones. So x bar, y bar, or x apostrophe, y apostrophe. And that's it. This one has two outputs of 1, so the function I write is going to have 2 terms. The min term for this second row with an output of 1 would have to be x bar y, right? So I'll put x apostrophe y plus, and then for this last term with the output of 1, just xy. They're both 1 already. And I mean, I know you can probably tell me, hey, isn't this the same as y? Yeah. I mean, you could use a law here to pull out the y, and then x bar plus x would be 1. 1 times y is y. This is equivalent to y. See how it has the same outputs as the y column, but they're not asking you to write that. They're not asking you to simplify. They say they want you to write it in the sum of min terms form like this. Alright, now here's one with 3 variables, right? So every single term is going to have an x, y, or z, or x bar, y bar, z bar, x apostrophe. And I think it just gets slowly more complicated. I think so the last 3 look like they just have 3 variables. Right. Okay, so simple enough, I feel. Writing functions given input-output tables for these Boolean functions. Alright, then you have your additional exercises. Again, some of these, I think most of these are on your assignment 6, if not all of them. And I would still recommend, though, even if some aren't assigned in assignment 6, I'd still recommend trying all of them. Get more familiar with the material, get more practice in. It's the only way to get better at anything. And you can view the solutions if you wish to see how you're doing. And as I say every video, don't just copy the solutions. Right? Try to work on these problems, try to figure them out before you look at the solution. Okay. And yeah, that's it for 5.2, this intro to Boolean functions here. Of course, if you have any questions, let me know. And thank you very much for watching.